Okay, so welcome everybody to this week's session. We are recording now, so if you can, please just type your name into the chat so that we have your record for attendance. So please type your name into the chat for attendance. Attendance, I think I spelled that wrong. Attendance. I think that's right. Okay, yeah. So everybody can type your names in. I hope everyone had a good week. We're going to finish today. We're going to finish up our statistics unit, which we spent, basically this whole semester on so far. So today will be the last day for statistics, and then next week we're going to start again with geometry. Okay. So I've muted everybody. Please only unmute yourself if you have a question to ask or if you want to answer something. Otherwise, staying on mute is better so that we don't get the background noise from everybody here. So yeah, just again, a reminder to write your name down for attendance if you haven't done that already. And good. So let's start off the same way we generally start off every week by going over the homework. This was nice. I think several people sent me homework answers this week. And these answers tended to be correct. So let's just review. Well, so this homework exercise 1 was the basic thing. We wanted to calculate all of these measures of dispersion for this data set that was just 1, 2, 3, 4, 5, and 6. And maybe before we do the homework exercise, let's just recall how we do, well, the range is easy. The range is just the maximum data entry minus the minimum data entry. And then we also talked about mean absolute deviation and about standard deviation. So let me just recall what this is. So remember, this is how we do the mean absolute deviation here. So if we have a data set, x1, x2, all the way up to xn, so we have n entries. And if the mean, the arithmetic mean, we call it x bar, then the mean absolute deviation of the set is the average of all of the absolute distances from data entries to the mean. So you can think of this as the average distance from the mean. So like for a given entry, how far away from the mean do we expect that to be? So that's the mean absolute deviation. And then recall also the standard deviation, which is a little bit more complicated, but is also used a lot more, is our setup is still the same. We have x1, x2 up through xn. So we have n data entries, and the mean is we also call it x bar. And then what do we do? Instead of taking the absolute values and adding them all up and dividing by n, instead we take all of the entries minus the mean and we square them all. And then you add those all up and divide it by n. So you're basically taking the average of the squares of the distances from the mean. And then once you take that average, because you squared everything, you then have to take the square root in order to get it to go back down to the standard deviation. Okay, so these are just the slides that we had from last time. This is recalling how to do the mean absolute deviation and the standard deviation. So now let's go back and actually look at our data set. So what do we have here? We have this data set. In this case, is just 1, 2, 3, 4, 5, and 6. And we're trying to calculate all of these different measures of dispersion. So the first one, which is the easiest to do, is the range. So what's the range of this data set? Somebody?
Yes.
Yes. Whoever is speaking?
Armstrong.
Armstrong, yes.
Yes. The range will be 6 minus 1.
6 minus 1, exactly. So 6 minus 1 is going to be 5.
5.
Right, and the way we got this is that this is the maximum entry in the data set, and this here is the minimum entry in the data set. Okay. Okay, so the range is very straightforward. I think most people will agree on that. So now, what about the mean absolute deviation?
Yes.
Yes. Yeah. Do you want to continue, Armstrong?
Yeah. Before we find the mean absolute.
Yes.
We have to find the means.
Right.
Before we find the means absolute. deviation.
Great.
So we say mean equal.
Mm-hmm.
Yeah, 1.
Yes, I mean, yeah, 1.
2. Yeah, plus 3.
Mm-hmm.
Plus 4. Plus 5. Plus
Yep.
6. Odd or 6.
Right. And this comes out to
which is
be
equal to 21.
right.
21 or 6
Mm-hmm.
is equal to 3.5.
Exactly. So this is 7/2, which is 3.5. Okay, great. So the mean is 3.5. That's great. That's the first step for doing either the mean absolute deviation or the standard deviation, is that you have to calculate the mean. So in this case, the mean is 3.5. Great. So for the mean absolute deviation, then Armstrong, you can continue if you want to finish it up.
Yes. So we take the absolute value.
Yeah.
So be absolute 1 minus 3.5.
Right.
2 minus 3.5.
Mm-hmm.
3 minus 3.5.
Mm-hmm.
4 minus 3.5.
Mm-hmm.
5 minus 3.5.
Yep.
Then we got 6 minus 3.5.
Great. That whole thing is going to be divided by 6. Divided by 6.
6.
Yep.
Yes,
we don't really want to round it. By the way, James asked a question. Can we round it off? We don't want to round off in the middle of the calculation. At the end, if you need to make a rounding, you can round it, but you don't want to round in the middle of the calculation. Yeah, so keep going.
Okay.
Yep.
Yeah, we need to get -2, but is the absolute value, so we have positive 2.5.
Right.
At 1.5.
Mm-hmm.
0.5.
Mm-hmm.
0.5.
Mm-hmm.
1.5.
Mm-hmm.
And 2.5.
Right.
Or was 6.
Mm-hmm.
It's equal to 9. 9
yep.
or 6.
Right.
Which is equal to 1.5.
Perfect. Okay, great. So the mean absolute deviation here is 1.5. Yeah, if you round it off to 4, you're going to get your answer is going to be off a little bit. So it's definitely better to keep the mean as it is, keep it as 3.5. And so yeah, so we get the mean absolute deviation is 1.5. That means of these numbers from 1 through 6, the average distance from the mean is going to be 1.5. And we can kind of see that, right? Like sometimes it's 1.5, sometimes it's 2.5, sometimes it's 0.5. The 1.5 is kind of what's in the middle there. And so it shouldn't be that surprising that when you end up calculating this average, you get that your mean absolute deviation, meaning the absolute value of the deviation from the mean, is going to be 1.5 on average. Okay, great. So any question? This is completely perfect. Thank you, Armstrong. Any questions about the procedure here?
Yes, Doc.
Yes, Ed.
Oh, I'm looking at it in a horizontal form. I think it would be wise if we do it in a tabular form.
In a tabular form?
Yeah.
So, I see. So saying something like we have something like a table with like xi, and then here we would have xi minus x bar.
Yes.
So we have 1, 2, 3,
then we
4.
can find the standard deviation and so forth. We just go in the tabular form.
Okay, that makes sense. Yeah, so why don't we do that? And in this case, so for the other tabular form here, we can have xi minus x squared, right?
Okay.
So we already did this, right? So this here was 2.5, 1.5, 0.5, 0.5, 1.5, and 2.5. Okay, this is a good idea, right? And let's just remind ourselves that x bar equals 3.5 here. Okay. Okay, good. So actually, do you want to complete the table? Do you want to complete the third column of the table here that we'll use for, so this is going to be for the standard deviation. Okay, so what do we put in this third column of the table here? The 0.5, is it constant? I don't quite understand. I mean, it is a constant, it's a number. I'm not sure I understand the question. Well, in any case, let's keep going and finish up the table so that we can answer the question about the standard deviation. Okay, so what are we going to get for the squares of everything in this second column over here?
Yes.
Yes.
That is
Yeah, sure.
6.25.
Yeah.
2.25.
Right.
0.25.
Mm-hmm.
0.25.
Right.
1.25.
2.25. And
2.25, sorry.
yeah,
It's 6.25.
great. Okay, so for the standard deviation, what do we need to do? We need to take the square root of what we get when we average everything here in this third column. So we have 6.25 plus 2.25 plus 0.25 plus 0.25 plus 2.25 plus 6.25. Everything here divided by 6 because we have 6 different measurements. And so this becomes, I haven't done this. So what is this? 8.5, 9.
17.5.
Yeah, 17.5. Great. 17.5 divided by 6. And why don't we just do the whole thing? Have you done the calculation? So what does that come out to be when you do it all out?
2.916.
Oh, okay. So, but under here, yeah. So 2.916, right? And so the square root of that comes out to be
1.7076.
okay. So let's say 1.7076. Okay, great. And so one thing that we see here is that the standard deviation is always a little bit bigger than the mean absolute deviation. So I haven't proven that for you, but that is a fact that the standard deviation is always at least as big as the mean absolute deviation. So the mean absolute deviation here was 1.5. Standard deviation tends to be a little bit bigger. So in this case, the standard deviation is 1.7, roughly. But this is how we calculate it, and it's a little bit more involved because we've got a square, and then later on we have to take the square root. So it takes a little, one extra step compared to the mean absolute deviation. And remember, the question didn't ask for the variance, but if you want the variance, it's just what you get under the square root before taking the final square root. So the variance here would be 2.916 with a bar over it. Okay, so this is a relatively straightforward example where you can do the computation by hand for all 3 of the major measures of dispersion that we're calculating. Okay, any questions about this standard deviation calculation? Okay. So let's go and continue with the next exercise, which is a little bit more conceptual instead of computational, right? So the next exercise is what happens to the range, the mean absolute deviation and the standard deviation of a data set if all of the entries are increased by 5? And what if all of the entries are multiplied by 5? So let me just divide this into 2 parts. So here we're going to have increase by 5. And here we're going to have multiply by 5. So let's start out. If we increase everything by 5, right? So the range, we're going to add 5 to the maximum entry, and we're going to add 5 to the minimum entry. So what happens to their difference? Yep. Anyone want to answer? So what happens to the range when we add by 5? Yes?
The range will still remain the same. Yeah, the range will still remain the same.
Exactly, right? It remains the same. right? I mean, I'm not going to write out a full proof, but I mean, if you look at this data set, right, we had 6 minus 1. If we increased everything by 5, the 6 would just go up to 11 and the 1 would just go up to 6, but their difference would still be 5. So you have your range, you increase everything by 5, you're kind of moving it over by 5 units, but that's not going to affect this distance between the maximum and the minimum part of the range. Okay, so the range does not change when you increase everything by 5. Okay, what about the mean absolute deviation is maybe not quite as straightforward. Put that there, and then I'll put standard deviation here. And well, maybe to answer this question about the mean absolute deviation, let's go back and look at our table, right? What are our inputs into the mean absolute deviation? It's these quantities, xi minus x bar. So if you increase all of the data entries by 5, then the xi's are all going up by 5. Well, if you increase everything by 5, what happens to the mean of your data set? So if you increase every entry by 5 in a data set, then what happens to the mean of that data set?
Can you please go
Yep.
on the question?
Sorry, so just go on, right? So if I'm just asking an intermediate question, which is if I increase all of my entries by 5 in a data set, then what happens to the mean of that data set?
Yes, let me try.
Yep. Mm-hmm.
The mean will increase.
The mean will increase, and by how much?
Let me see. 100.
If you add 5
okay.
to all of the data entries, then what gets added to the mean? Also, yeah, so James answered right, by 5. Exactly, right? If every single entry is increased by 5, that means the average is also being increased by 5. Okay? So what we have here is a bunch of xi's. These are our data entries. These all get increased by 5, and the mean itself gets increased by 5, which means when we subtract them, right, nothing changes at all, right? So if we increase all of our xi's by 5, in this column, everything stays completely the same, right? Because the mean goes up by 5 and the entries go up by 5. And over here also, everything stays the same, right? Because the mean goes up by 5 and each of the entries goes up by 5. So let me just write that down. So first observe, we know that this goes up by 5. So xi minus x bar stays the same. Okay. And what that's going to mean, well, if this quantity stays the same, and this is your input into the mean absolute deviation, right? The mean absolute deviation is just the average of all of these quantities. So if all of these quantities remain the same, then the mean absolute deviation has to so the mean absolute deviation, it has to also remains the same. Okay. Because the point is the mean absolute deviation is the average of all of these quantities. Okay. And if all of these quantities stay the same, if they don't change at all, then the mean absolute deviation can't change at all either. Okay. So we see here is that when you increase all of the entries by 5, nothing happens to the mean absolute deviation. Okay. Okay, questions on that? Okay, so let me quickly, just because I want to make sure we get to the new stuff, for the standard deviation, this is going to also remain the same. And, the reason here is that, well, if we look at what is the input to the standard deviation, it's all of these quantities, the square of xi minus x bar, right? Xi minus the mean. Well, if you increase all the entries by 5, well, this gets increased by 5, the mean, and each entry gets increased by 5, which means their difference has no change at all. So all of these quantities that are the inputs into the calculation for standard deviation, none of them changes at all. And so if none of them changes at all, that means that the standard deviation also doesn't change. So it's basically for the same reasons as the mean absolute deviation not changing, the standard deviation also doesn't change. Okay, so what we see is if we increase the entries by 5, then all of these measures of dispersion stay exactly the same, right? And that makes sense, right? Because they're measures of dispersion. If I have a whole data set and then I just shift it over by 5, it doesn't do anything to how they're dispersed, right? It just has shifted them all over. They're not any more or less spread out than they were before, right? So it makes sense that if you take all of the entries and you increase them by 5, then nothing happens to any measure of dispersion, right? Okay, so any questions on what happens when we increase everything by 5? Okay, so I'm going to go through the multiply by 5 kind of quickly, just because I want to make sure we have enough time to do the new topics for today. And I can't really run over today. So let me just say briefly, what happens to the range? Well, if the old range is the maximum minus the minimum, when we multiply everything by 5, the new range, the new maximum element is 5 times the maximum minus 5 times the minimum, which is equal to 5 times the old range. Okay, so what happens with the range is that it gets multiplied by 5. So if you multiply all of the entries by 5, then the range also gets multiplied by 5. Okay. So that's what happens with the range. What happens with the mean absolute deviation? Well, let me just say it. What we really care is what's happening to all of these entries. Well, if every entry here gets multiplied by 5, so all of the xi's get multiplied by 5, the mean of the data set will also get multiplied by 5. If you multiply every entry by 5 in a data set, then the average also gets multiplied by 5. So this gets multiplied by 5 and this gets multiplied by 5, which means the entire quantity in this column also gets multiplied by 5. So everything here is getting multiplied by 5. And if the mean absolute deviation is the average of all of the entries in this column, and every single one of these entries gets multiplied by 5, then the average also has to get multiplied by 5. So the conclusion here, maybe a little fast, the conclusion is that the mean absolute deviation also gets multiplied by 5. Okay. And lastly, let me do the standard deviation. Well, what happens here? All of these xi's get multiplied by 5. The mean also gets multiplied by 5. So the quantity in the parentheses here gets multiplied by 5. But then you're squaring it. And if you multiply the inside here by 5 and then you square it, the square actually gets multiplied by 5 squared, which is 25. So everything in this column will get multiplied by 25, not just by 5. And so what happens when we do the standard deviation, we're taking the average of all of these things that are all multiplied by 25. And that means the average will also get multiplied by 25. So the average gets multiplied by 25. That tells you the variance gets multiplied by 25. But in the end, with the standard deviation, you're taking a square root. So if you have your original quantity multiplied by 25, and then you take the square root of that, that actually means that compared to what you got originally, you're only going to multiply it by 5. Okay, so if your variance gets multiplied by 25, since you're taking a square root, your standard deviation will only get multiplied by 5. Okay, so at some point, maybe I'll write this up a little bit more carefully. I don't want to do that right now. Maybe I'll send it later, just because I want to make sure we have enough time to move onto the new topics for today. But it turns out that the standard deviation here also gets multiplied by 5. Okay. So what we see here is all of these measures of dispersion. What happens? You have your data set. You multiply everything by 5. What does that do? It actually spreads out the data set a little more, right? If we started with 1, 2, 3, 4, 5, 6, you multiply it by 5, you now have 5, 10, 15, 20, 25, 30. That's more spread out than 1, 2, 3, 4, 5, 6, right? So, and we see that reflected in these measures of dispersion, that if you multiply all the numbers by 5, you're kind of making them all 5 times as far apart from each other. And the way that happens, what that results in is that for these measures of dispersion, they all get multiplied by 5 also. Okay. So I know this, I did that a little bit fast and I didn't really write anything down. I will try to write down a full proof of it later that I'll send out. But I don't want to spend too much more time on this. So I can maybe take one question about this multiplying by 5 stuff, and then I want to move on to the new topics. Okay. All right. So any last questions about this? Okay. Okay. So let's move on then. Okay. Where are we? Okay. So let's move on to the new topics. Okay, this is just recalling here. Okay, so I want to say one more thing about box and whisker plots. So remember we talked about these last time. This was a way of visualizing data that was based on percentiles. And we had that a box is drawn parallel to an axis. Usually it's drawn vertically, and we stretch it from the 25th to the 75th percentile. The length of this box, we said last time, is called the interquartile range. And we draw a horizontal line at the 50th percentile, or the median of the data, and we have that whiskers extend above and below the box to the maximum and the minimum of the data points, respectively. And then you can read off the range and the median of the data directly from the box and whisker plot. The median is exactly where this line is drawn at the 50th percentile. Let me recall, that is, this 50th percentile is the median. And then the range, because we have the whiskers that go up to the maximum point and down to the minimum point, then you can also read, whatever that distance is the box and whiskers plot. So give me a second. Okay. Okay. All right. So remember, we had this data set last time, and I just want to recall exactly, what we had. So last time, what did we have? We had n. There's 32 measurements here, and we calculated the percentiles last time. So let me just recall this. The 25th percentile was I think it was 62. We did this all last time. The 50th percentile was, so that's 8, was 71, and the 75th percentile was So the 75th percentile was 76. Okay, and then we also have the max was equal to 100, and the min was equal to 45, right? Okay, and so the minimum was equal to 45, and so we had our, and I'll just draw our little box and whisker plot by hand. So I'm just going to mark everything by tens up to 20. So 30, 40, 50, 60, 70, 80, 90, and then up to the max to 100. Okay, and how did the box and whisker plot work? I have to draw the box from the 25th percentile up to the 75th percentile. So this goes from 62 up to 76. So I'll draw the bottom of my box over here, and the top of my box, well, maybe it should be more like this. Okay. And then I draw a line at the median, the 50th percentile, right? I draw my median. Okay, so that's going to be right here. And then I drew the whiskers going up to the maximum and up to the minimum. So the maximum went from 76 up to 100. And then the minimum went from 62 all the way down to 45. 45. Okay. So this was my basic box and whisker plot, and we did this the last time. Okay. I'll pause. What I want to do today is show you how to do it on a computer, and also show you a couple of variants of box and whisker plots, and then we're going to do standard deviation for group data, and that'll be it for today. But before I go on to that, any questions about how this box and whisker plot works? Any questions? Okay, so let me say something about variations that we have on box and whisker plots. So sometimes instead of having the whiskers extend to the maximum and the minimum values, you don't go all the way up to the maximum and all the way up to the minimum, but you only go up to a length of 1.5 interquartile ranges from the edges of the box. N32, N is just the number of entries here. So that if you count how many entries there are 32. Okay. So that N usually just means 32 entries. Oh, sorry, 31 entries. You're right, 31. Thank you. That's a mistake. N should be 31. So there should be 31 entries. Okay. Thanks. Sorry about that. Yeah, so it's 31. Okay. So sometimes in your box plots, you only go up to 1.5 interquartile ranges from the ends of the box. This is a pretty standard convention. You'll see this a lot. And in particular, this is the default setting that Microsoft Excel uses when it creates box and whisker plots. Okay, so if we work it out by hand from the above data, what do we have? Well, we have the interquartile range.
Hello.
This question? Yeah, Manuel?
Are you getting? Yes.
Yep.
Actually, I was trying to. I'm asking concerning the 25% of 62, 50% of 71, and 75% of 76. How do you arrive at that, sir?
Oh, it's not percent of. This is percentiles. So this means the 25th percentile of the data is 62. And the 50th percentile of the data is 71, and the 75th percentile of the data is 76.
Okay.
Okay, so we did these calculations last week.
Okay. Thank you.
No worries. Right. So what happened? What's the interquartile range? Remember, that's just the 75th percentile minus the 25th percentile. So in that case, it's 76 minus 62, which is 14. So in this case, the interquartile range is 76 minus 62, which is equal to 14. And what we need to calculate, which is the usual convention, is 1.5 interquartile range. So 1.5 times interquartile range is equal to 1.5 times 14, which is equal to 21. Okay. So what do we do? So if we wanted to do a modified box and whisker plot, so this is general plot. And now side by side, if I wanted to do a modified plot, which is going to be the same, except that I don't let the whiskers necessarily go all the way to the top or all the way to the bottom. I only let it go up to 1.5 interquartile ranges, which is a distance of 21. So what that means is, so maximum allowed is going to be the end of the box, 76, which is the 75th percentile, plus 1.5 interquartile ranges. So the maximum allowed in this case would be 76 plus 21, which would be 97. And the minimum allowed is the 25th percentile, that's 62, minus 1.5 interquartile ranges, minus 21, which would be 41. Okay, so what this says is that when we're considering our maximum and our minimum, the highest we're allowed to take our maximum is 97, and the lowest we're allowed to take our minimum is 41. Now, that doesn't mean we actually use 97 and 41. What it means is that we use the maximum and minimum data points that are in this range of 97 and 41. So what we say is that the maximum allowed data point is 97, but what we actually do is we just take our biggest data point that's less than 97. So if we look at the data over here, what's the largest data point that's less than 97? What this is basically telling us is that we're not allowed to use these 100s. They're too big. They're more than 1.5 interquartile ranges above the 75th percentile. So they're more than 21 above 76. So we have to use the next biggest data point, which is 88. Yeah, so 88 is going to be what we actually use for the maximum in this new modified box and whisker plot. Okay, so the max allowed is 97, and that tells us that the actual whisker goes to 88. Okay. So similarly here, the minimum allowed is 41. What happens? Well, if we look at our data set, actually the minimum is 45. So we're not going to draw the whisker all the way down to 41. We're just going to use the minimum data point that is no less than 41. So in this case, we actually will just go down to 45. It will be the same as the minimum from the original box and whisker plot. So the actual whisker here, so the actual whisker goes to 45. Okay, so when we do our modified box and whisker plot, it's going to look the same as the original one. The only difference is that the maximum whisker won't go all the way up to 100. We're considering that too far an outlier. It's more than 1.5 interquartile ranges from the 75th percentile. So we think of these hundreds basically as mistakes. We don't want to write them in the data set. There may be measurement mistakes or something. So what we actually do is we just go up to 88. And then the minimum whisker will go to 45. So if we look at it, it's going to look almost exactly the same. The box doesn't change when you do this modified plot. So you still have, 62. You can always label these if you want, 62, 71, 76. And then the bottom whisker will still go down to 45, but now the top whisker will only go up to 88. So it'll only go up to 88. Okay, so this is the modified plot, and this is what we're going to do it on a computer next in Microsoft Excel, and this is what Excel actually does. Okay, it only gives you the modified plot. It only goes up to 1.5 interquartile ranges from the 75th percentile, and only down 1.5 interquartile ranges from the 25th percentile. Okay, so just to recall this, right, you have to calculate the interquartile range, multiply it by 1.5, and this gives you kind of an upper bound and a lower bound on which data points you're allowed to consider. And then you do your box and whisker plot, but you don't consider data points that are outside these bounds. So we only consider things between 41 and 97, which means that these 100s over here get eliminated when you do this variant of the box and whisker plot. All right, so any questions about this kind of methodology? Okay. All right. Okay. If there's no questions about this, let me let me show you how to do this in Excel. So Microsoft Excel can draw you a box and whisker plot. And so there's 5 steps. So you have to put the data in a column on a spreadsheet. And then you highlight the column using the mouse or the keyboard. Then you have to click Insert on the main menu, which is at the top of the screen. And then you have to, sorry that this changed. Oh, no, sorry. So 1 second. Sorry, I have to do this. Let me join my meeting. Let me just get this. Sorry, I got kicked off. 0.14159. Sorry, I had a little technology problem. Do this. I'll make myself co-host. Give me a second. Where am I? Okay. Okay, sorry about that. Let me do a share. What do I want? Okay. All right, we got this now. Okay, so good. So this is where we were. Sorry about that. So we click Insert on the main menu at the top of the screen, and then there's the statistical chart icon. We're going to click. It looks like a histogram, and then we select box and whisker plot. Okay, so let me do this. I'm going to open up Excel. Do this. Going to open up Excel. Here we are. Okay. Okay, so it's going to take Excel. Okay, so let me see. Okay, let me do a blank workbook. Okay, and so I'm going to show you my Excel screen then. Let me go to Zoom. Okay, share screen. Let me go to Excel. Okay, so the first thing I'm going to do is type all of the data into a column. So we had 45, 48, 50. So 45, 48, 50, 54, 50, 54, 57, 60, 60, 62, 63, 63, 64, 65, 67, 68, 69, 71, 71, 72, 72, 74, 74, 75, 75, 76, 80, 83, 84, 88, 100, 100, 100. Okay, so we have this data. That was step 1. So step 2, I'm just going to highlight it over here. And now I go to Insert. And when I go to Insert, my my screen gets all of these little icons. And I click this one that looks, it's called statistical. It looks like a little blue histogram. So I click the arrow there, and we see it has box and whisker plot. So I just click on box and whisker plot, and voila, and it's all there, right? And so what we see, let me make this a little bit bigger so that it's a little easier to see. All right, so just to make it a little bit bigger. And so what do we see here? We have exactly what we saw, what I drew by hand. The 25th percentile here is 62. You see the axis here. Here it's done 20, 40, 60, 80, 100. The 75th percentile is 76. With this little line here at the median, this is at 71. I mean, it even tells you. And then what do we have? We have the bottom one going all the way down to 45, the bottom whisker, and the top whisker goes all the way up here to 88, right? This is exactly what we found by hand. And then it also marks just a little dot here for the maximum value for the 100. It's just an extra dot to kind of mark that this is an outlier measurement. Okay, so the actual plot only goes up to 88 because it will only do 1.5 interquartile ranges, but it'll also mark a little dot here at 100 to just remind you that actually there was some data above that, but we think it's an outlier. Okay, so doing box and whisker plots on Excel is pretty easy. You just have to type in your data and follow the steps, and so those steps are there in the on the slide, so it shouldn't be too bad. All right, so any questions about doing this in Excel?
Yes, Doc.
Yes, question, Ed?
Yeah, after we go to, okay, because I'm looking at your screen, your Excel screen.
Right.
After you put in the data entry, you highlight, and then you go to Insight.
Yeah.
Right? Then after Insight, what you go to?
This one that looks like a blue histogram, it's called the statistical charts. So you click on this little arrow here, and that gives you the option to just do a histogram, or you can do a box and whisker chart. And so you click on the box and whisker chart.
Thank you. Thank you,
All
I
right.
just sorry.
Oh, no problem. You're welcome. Yeah, it's a little hard because I liked it when the old versions of Excel had pull-down menus with words, and it was easier to find things. Now it gives you these pictures, which I actually don't really like because it's hard to tell what's what. But for box and whisker, you have to go to this blue histogram. If you have an old version of Excel and insert just gives you a menu with some words, then I think statistical is the word that you actually click on, and then it will give you box and whisker as an option. Yeah, so here's like pie chart, line graph, column, hierarchy, statistical, XY scatter. So I think statistical is what you want if you have an old version of Excel and it's a pull down menu. Okay. All right. Okay, so let me close Excel and we'll do the last topic for today. So let me reshare my screen over here on Zoom. So share screen, broadcast. Okay, great. Where's my screen sharing? Okay, should be here. Okay, so this was over here how we drew everything on Excel. So I'll send those sheets over with the notes on the chat. So if you forget, you'll be able to look it up over here. It's just 5-step process, pretty easy. Okay, so the last thing that I want to do is, and this was, somebody asked me this last week, maybe it was Ed, I don't remember, or Gabriel, somebody asked me this, how to do the standard deviation of group data. Okay, so suppose we're given group data in a frequency table where each row of the table corresponds to a range of values. So how do we calculate the standard deviation in that case? Well, we've already seen how to calculate the mean of the data. The way that we calculate the mean of the data is we look at the midpoint of each class, and we take a weighted average of these midpoints weighted by the frequency of each class. So let's say that we have the mean, and we'll call it X bar like usual. So what we do now, if we let Xi be the midpoint of the ith class, and we let Fi be the frequency of the ith class, so each class has a midpoint and a frequency, and we let capital N be the total number of measurements. We know that the total frequency is the sum of all of the individual frequencies. Then the standard deviation, you can calculate it with this formula, which looks a lot like the formula for the original standard deviation, which is that you take all of these midpoints and you take the difference from the mean and you square it. And instead of just adding it up, you have to multiply everything by the frequency before adding it up. And then you divide out by n, by the total frequency, and then you take the square root of all that. And that's going to be the standard deviation. So it's got an extra step or two when you have these frequency, when you have data grouped instead of having individual things. So it's kind of the same, but you first have to calculate this group mean, and then you have to calculate the total frequency, and you have to calculate all of these midpoints, and then you've got to do all of these differences and look at the frequency and square them and do all this together, okay? So this will be very good to do it with a tabular method. We're going to put it all on the table. We'll do one example of this. And I think, with the formula is kind of maybe just hard to understand by looking at the formula, but it will become a little clearer by doing an example. So this is still our favorite example that we've had, where we calculate the standard deviation of the group data. So this is the group data that was commuting time for people who lived in a certain California jurisdiction. I think we've used this data set a bunch already this semester, and I want to actually see, I think we already calculated the mean of this, which I'd like to just write down instead of doing the calculation again. So did we calculate the mean of this group data? Was that on 11.3, or was that, trying to remember, that wasn't, we didn't do that. Maybe it was an earlier day. Let me see, handout on 10/27, did we do it then? Yes, okay, so we calculated the mean of this group data, and it was 17.62. So I'm just gonna write this down. So we calculated this X of this group data, this bar, on October 27th, if you wanna go look back at the notes, and it was equal to 17.62. Okay. So now we're going to have all of our data set. We're going to write down everything that we need. Sorry, we're going to write down everything that we need in order to get the information. So for each class, we need its midpoint, which is the xi, and we need its frequency. And then we need to multiply them all together. So let me write down, we'll write down a table. Okay, so it's going to have a few columns. So it'll have its frequency, its midpoint, and then its frequency. And then over here in this column of the table, we'll have the frequency times xi minus x bar squared. Right, so these are going to be kind of the three parts of the table that we really need. Right, because this fi times xi minus x bar squared, this is what gets fed in to this sum, right? So in this case, our midpoints are easy. We calculated these already. For the midpoint, we just take the two endpoints and we take their average. So this is 0 to 5, 5 to 10, and so on. So we just go 0 plus 5 divided by 2, that's 2.5. So we've done this already. Our classes are going to be 2.5, 7.5, 12.5, 17.5, 22.5, 27.5, 32.5, 37.5, and 42.5. Okay, these are, so the frequencies are just the same frequencies that we read off from the table. So this is just 5,200, 18,200, 19,600, 15,400, 13,800, 5,700, 10,200, 2,000, and 2,000. And I think we saw already on the previous day that the total number of entries was, I think it was 90,200, something like that, or 91,200. Let me just write that down. The total number of entries was 92,100. So this capital N we calculated before was 92,100. Okay, so now we need to calculate all these squares. I'm just going to do the entire calculation at once. I'm just going to write it down over here. So I'm just going to give you the answer. So remember, it's xi minus x bar, right? So this x bar is equal to 17.62. So I'm going to have 5,200 times 2.5 minus 17.62 squared. Oh, so this is actually going to be a long, some of these numbers get pretty big. So I'm going to give a little bit more space. So I'm going to round these to the nearest integer. So this is 1188795. I'll use 7.5 here instead with 18200. So this is going to be 1863942. Then 12.5 and 19600. This is going to be 513802. 17.5 times 15400. This is going to be just 222, very small. Then 22.5, and this is going to be 13800. So this is 328,639. Then I have 5,700 with 27.5. This is going to be 556402. Then we have 32.5 and 10,200. This is 2258427. Then 37.5. This is going to be 2,000. This is going to be 790429. And then lastly, this over here is 1238029. Okay, so I'm just doing these calculations. I'm just plugging everything in. I take the xi, I subtract 17.62, I square it, and then I multiply it by the fi. So this is what I get over here. Okay. And so now we just have to go back and see the formula. What do? I take all of these entries, I add them up, and then I divide by 92,100. So what we have is that the standard deviation, I'll write SD, is going to be the square root of, 1188795 plus, and I won't even write them all down. And then at the end, 1238029, all of this divided by n, which is 92,100. And then I take the square root of what that comes out to be. So let me just do this. So first, if I have square root of, so 1188795 plus 1863942 plus 513802 plus 222 plus 328,639 plus 556402 plus 2258427 plus 790429, and then plus 1238029. If I do this all and I divide it by 92,100, so at some point you can check this on a calculator, but what I get here is a standard deviation of 9.74. So this comes out to be roughly 9.74, right? Which is a good, believable answer, right? Because remember, what is the standard deviation supposed to represent? It's still it's some way of representing, on average, how far are you away from the mean. So if the mean here is 17.62, and we have all of these things ranging from 0 to 45 in various frequencies, it doesn't seem that hard to believe that on average, you're about 9.74 away from the mean. That would be, being at about 8 on the low end and being at about, 27 on the high end, right? Which seems reasonable. That's where a lot of these this data is clustered. Okay, so calculating standard deviation for group data can be a little bit annoying. There's a lot of calculations to do, but you just have to follow the formula. And the key is calculating this quantity. First, you have to calculate the mean, which we did 2 weeks ago. And then you have to calculate this frequency times the distance from the midpoint to the mean squared. And once you have all of that, you just add them all up together, divide by the total number of measurements, and then take the square roots. And you end up getting, this is your group data standard deviation. Okay, so if you want to check my work after class, you can do that, and you'll get 9.74. Okay, so any questions about the procedure here? Okay, anything? Okay. Okay, good. So that's basically it for today, and that's going to wrap up our statistics unit. So for the homework exercise, you have a smaller scale version of this. So let's say that we have a frequency table given by these entries. So these classes go 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50 with these frequencies. Then try to calculate the mean and standard deviation of the group data. Let me just recall for you, for the mean, if xi are midpoints, then the mean by definition is the sum of the fi times the xi. So each xi gets multiplied by the frequency and then divided by n, where this n is the sum of the frequencies. Okay, so to try to calculate the mean and the standard deviation of this group data. So this is kind of the culmination of everything we've done with statistics. So that's it for statistics. So thank you very much for your attention. And next week, we will begin our unit on geometry. Okay, so we're going to be finished with statistics, and then we're going to go do our unit on geometry. Okay, so any last questions here?
Yes.
Yes,
Hello.
Emmanuel?
Yes.
Yeah.
Are we to get this material on the group chat?
Yep.
So that I was trying to copy the assignment that you really can do.
Yeah, I will. Later this afternoon, I will send all of the slides to the group chat as a PDF, so you'll be able to look at it.
And another question in solving the standard deviation
Yep.
of the group data, do we have another way of solving it so that our students can get it quicker?
I don't know. So you can tell me what it is. This is the only way that I know to do standard deviation of group data. I mean, of course, this data is a little complicated, so it takes a long time. By the way, Armstrong, it's you square only the xi minus x bar, and sorry, you square only this part, and after you square it, you multiply by the fi. So if you need to see it in a little bit more, it's fi times xi minus x bar squared, and I'll put extra parentheses here just to say the fi does not get squared when you do this. But yeah, I don't really know any better way to do standard deviation of group data. It's just it's a fairly complicated procedure. I don't really know a simple way to do it.
Okay, then another thing will be, you got me?
Yep.
How can we how can we apply this concept to everyday life?
Okay, well, I mean, in general, I mean, everyday life. Sorry, there's too much feedback. Sorry. So for everyday life, I mean, usually more this is going to be applied in some sort of science or in some sort of statistical study, right? I mean, what you need to know is like what standard deviation means, right? So standard deviation means that Standard deviation is telling you how far certain is telling you how far you know, an average how far an average measurement is away from the mean. So if you're given group data, you're given group data, right? I mean, so this is somehow, if you're reading something where this is being reported in group data, what it's telling you is if the standard deviation is very small, then that's telling you that basically all of the data is very close to each other. And you can expect further instances of this data to all be very close to the mean. Okay, that's what a small standard deviation means. It means that everything is very, very close to the mean. So you have a high level of confidence that if you see more data, it's all going to be very close to the mean. If the standard deviation is large, then what that's telling you is that the data is all over the place. So for instance, if you have a class and you're giving an exam, and you have their standard deviation that you're calculating, if the standard deviation is large, it means that your class performance is really all over the place. There's lots of people with very high scores, lots of people with very low scores, and you have a very large range of your performance in your class. Whereas if your standard deviation is small, it means that basically everybody in the class did the same, or did almost the same on what they're doing, right? So this is what standard deviation means. It's telling you how spread out all of your data is. Okay. Okay, other questions?
Okay. Hello,
Hello, yes?
Emmanuel again. I'm sorry.
Yep.
My final question is about the absolute deviations and standard deviation. Yeah, I'm sorry I wasn't in class last week. Can you throw a little light on the absolute deviation and standard deviation?
Sorry, what's the question?
Absolute deviation and standard deviation.
Right. So there are two different measurements of dispersion. And the absolute deviation is always a little less than the standard deviation. They both kind of measure the same thing. The standard deviation, at least in advanced statistics, tends to be a much more well-behaved quantity. So like the standard deviation, if you read any serious scientific paper, what they're always going to report is the standard deviation, not the mean absolute deviation. The absolute deviation is a little easier to calculate, but the standard deviation, I think most people think it gives a better representation of what the dispersion is. So it's a little bit harder to calculate, but I think most people think that it's a better measurement.
Okay, thank you.
Yep. All right. Okay. Other questions?
Hello.
Hello, yes, Sange?
Yeah.
Okay, I'm going to stop.